All right, thank you everyone again for joining this CelerData webinar. This is our first for the APAC time zone. So really nice meeting you guys. So today's topic is on real-time analytics for Web3. We're gonna talk about fraud detection, trading and growth, how to do them at a scale. Hello everyone, I am Cedar Shen. I am a product manager at CelerData, also a StarRocks contributor. So here, let's quickly go over the agenda. So first, we're going to talk about Web3 and its use cases, mainly to do those analytical use cases. And then we're going to talk about the general challenges with Web3 analytics. And then we're going to talk about some of the architectural decisions, what you should be looking for, to overcome those challenges when building analytical function for your Web3 analytics. And then we're going to talk about how to achieve these requirements: low latency, scalable joins, real-time mutable data, and more. And then we're going to talk about some real-world use cases from industry leaders in the Web3 world, such as Coinbase, and more. Okay, so now let's get started. So Web3, I'm not a Web3 pro, but I think Web3 is moving us from a centralized platforms to decentralized ownership, right? Where the user actually own their own data, their identity, and digital assets without a centralized platform, ruling everything, right? So the user own everything himself, and it's very, very transparent. It's built based on open technologies such as blockchains, smart contracts, open core protocols, right? Enables a trustless collaboration. Basically means that there's no like one big gigantic platform you need to trust, right? You need to build that trust with because everything is the user owns everything, right, on the blockchain. Full transparency into everything and real-time value exchange on top of all of this, right? So having a open and decentralized platform, it does not mean we don't need regulation, right? We still want to perform anti-fraud and regulatory tracing, right? And on blockchain, so it's basically these scenarios, right? So we want to build trust. We want to ensure transparency. We also want to protect users, in this decentralized financial systems. So first, we want to do anti-fraud and anti-money laundering, right? We want to detect those suspicious transactions and to ensure compliance, right? And this is often multiple chains through multiple hops, and this is very 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 expensive to do this kind of tracing. So the requirements, right? So first we need for those anti-fraud and regulatory tracing, we need real-time visibility. We want to be able to detect and respond, within seconds, not minutes, not hours. And then we want traceabilities across multiple chains and multiple hops. And this is very difficult to do, right? So tracing is like searching through a not tables, not tabular data, but actually like a graph, like a directed graph, right? And each trace you can think of each step, right? Each hop you can think of as a self join, right? And the number, the number of rows of data that involve in the self join explodes, exponentially with the number of hops you do. This is very very expensive, right? And with all of that, we want performance consistency. We want sub-second response time, even under really, really high load, right? Uh, Hundreds of transactions sometimes per second, right? And we want scalability too, to be able to handle terabytes to petabytes of data according to our users, right? And also on top of those, we want security. We want it to be tamper-proof, want it to be governed, and we want everything to be traceable, right? And apart from anti-fraud and anti-money laundering, we also want to, Web3 companies also looking for growth, right? User behavior analytics, and growth, understanding their user journey, right? Their user churn, where do they churn, and what do they actually do, on a daily basis, to improve user experience and to grow the platform, right? And then market and order book analytics, right? Delivering very high concurrency insights, into real-time trading. And then, it's risk control is, real-time operations such as, monitoring, right? This every single platform needs, especially for Web3, for blockchain, right? Where the transaction is, you cannot really make a mistake there, right? And there's a lot of transaction per second, right? Monitoring platform health and, prevent incidents. We don't want any of those to happen, right? And they come with their own sets of requirements too, right? So it's the first freshness. We want to process and create new on-chain data and operation data within seconds, and also concurrency, right? Many simultaneous data, your transaction data, and behavioral data, for the complete picture, right, of user behavior. So, we can have the best possible insight. And cost efficiency, right? To handle this is even more data, right, than the fraud detection. We want to handle crazy amount of data, right? Still at a sustainable cost, without very complex data pipelines. Okay, so let's wrap up, right? So the technical challenges for the underlying analytical database, right? So when you are picking a database, what are the things you need to be looking out for, right? So real-time ingestion, right? And not only real-time, second level data freshness, but you also want mutable data, right? You want to support all kinds of data. If you want to make a change, to the ledger, you want to be able to do that, right? So and many solutions that are available today, especially your real-time data warehouse, they still rely on merge on read, right? Real-time updates on those merge on read based systems actually impact query performance because the merge it never, in the background, it never catches up. Right? It will always affects the read. It's going to impact your query performance. So you want something that is able to take care of that second level data freshness with mutable data, with data upserts and deletes without impacting your query performance. And then is complex multi-table or join analytical queries, right? You want to run this kind of join queries, especially for the tracing scenario, right? You want to run those joins on the fly, and you want them to be run fast. And a lot of real-time data warehouse, they don't optimize for join. They rely on denormalization rather than the doing the join on the fly, right? Denormalization is very, very expensive. Expensive on the pipeline, expensive on schema change because you have to do data backfilling, right? If you actually change a column anywhere, you have to do data backfilling on the entire denormalized table, right? And the complex pipeline is very difficult to do real time because you have to do stream processing, to keep up with the data freshness if you want to do denormalization with real time analytics, right? And also high concurrency with heterogeneous workloads and multi-tenant, right? Um, it's very easy to see, one of those our users, scale to thousands of simultaneous queries out of many different kind of workload in one cluster, right? And you have to do those without, the different kinds of workloads, different kind of tenants, that competing with each other, for resources. So you make sure that all of your tenants and workloads always get the appropriate amount of resources, right? And cross source and format federation. We just talk about that, right? There are many types of data in blockchain, right? On-chain data, transaction, behavioral, many kinds of data, right? You want to be able to query across multiple formats. That's, let's say, JSON or some open Lakehouse format, such as Apache Iceberg, right? And just regular tabular data, right? Across those formats and different kind of engines, right? You want a unified view of all of your data that's available in your organization, right? So what we should be looking for, right? So first, a unified architecture. We don't want to separate real-time and historical data. That's really, really bad, not only for a data architecture, but more for a data governance, right? How do you keep the data in sync? That's a very, very difficult problem to solve, right? And also, you do want an elastic architecture, right? You want to be able to scale without actually moving data, without actually needing to wait, right? You can do that dynamically according to your workload, right? So scale efficiently, with compute and storage separated architecture, right? And high performance, you want your system to be optimized for low latency and high concurrency like workloads instead of something that this is designed to return the result in tens of seconds, right? You want it to be multi-tenant, multi-heterogeneous kind of workload friendly, right? You want to be able to isolate and balance workloads dynamically, right? Multi-source interoperability, we talk about that. Different kinds of format, such as Apache Iceberg, some unstructured, semi-structured data, and also streaming data, right? Be able to stream directly from your streaming sources to ensure data freshness, also with mutable data, right? And also you want governance and reliability. Be secure, you want to be auditable, right? Highly available by design, right? So here, let me introduce StarRocks that solve these problems, right? So StarRocks is one of the fastest or the fastest analytical database for real time, for Lakehouse, and for AI agent workloads. So it is a open source Linux Foundation project. It is built to run low latency multi-table queries on the fly without denormalization. It's built to handle thousands of QPS of analytical queries, and it supports real-time updates with some 10-second data freshness. Right. Also has full Apache Iceberg support, so you can run your low latency like workloads directly on Apache Iceberg on open formats without data ingestion. Right. So on the right are some metrics. 5 years we've been open source, 11,000 stars, around 500 contributors, and we're almost at 5,000 Slack members. Join Slack. StarRocks is trusted by 500 plus enterprises around the world, right? See Fanatics, you see Coinbase, and many other names here, right? Come a long way in the last 5 years. So there are two scenarios that StarRocks is very good at, right? So first is with real-time analytics. So to use StarRocks as a data warehouse. So in this format, in this kind of deployment, we're utilizing StarRocks optimized storage format, right? On the right-hand side, you see the data is persisted in the cloud object storage in StarRocks files governed by StarRocks tables, governed by StarRocks metadata, right? That is StarRocks' own optimized format, specifically optimized for real-time processing, right? So it's able to do sub-second queries at scale, right? Best-in-class performance on the fly joins, no denormalization. But the most important thing for the internal optimized StarRocks format is its ability to perform real-time immutable data directly on columnar storage. Can get down to around 10-second data freshness, with a lot of updates and deletes. And storage and compute separate architecture, everything persisted in an object storage, and everything the compute node CN, right, is the cache data, so it can be discarded any time. So you can, scale it in and out, without moving any data because all of the data is persisted somewhere else in the cloud object storage, like AWS S3. Real-time analytics and StarRocks is also fit into the data lakehouse architecture. We're going to talk about some use cases in the end from actual users, right? So StarRocks on the open data lake, instead of storing things in StarRocks' own format, you can discard the entire StarRocks storage format and basically hook it up with a Delta Lake table, Delta Lake tables, Apache Iceberg catalogs, or Apache Hudi, right? So directly query those lakehouse tables or open data lake formats directly without data ingestion, right? Supports all of the popular table and file formats. It is a newer generation of query engine, for the lakehouse. It's MPBU architecture. We're going to talk about those a little later, right? So basically, you're able to get data warehouse performance directly on your data lake tables, such as Apache Iceberg tables. Okay, so now we will talk about how we achieve, some of the things we just talked about, achieve and solve some of the challenges we just talked about. So first, how to run joins fast enough so you do not need to do denormalization, right? So first, to understand a query, right? So first, a query is planned, right? And then it sends, physical plan to your execution nodes, and the execution nodes execute, right? So that's basically like a very high level of how a query is run, right? Query planner is probably, I think, the most important thing for joins, right? Because join reordering, what kind of join algorithm to pick, what kind of aggregation methods, one phase, two phase aggregation, right? And what kind of distributed join strategy do you use? The search space for possible ways to execute a join query is enormous, right? So the difference between an optimized plan and an inoptimized can be like several orders of magnitude big, right? And the state of the art approach into solving these very complex multi-table join queries is cost-based optimization. What it does is instead of just basing on some heuristic rules, a cost-based optimizer will collect actual statistics periodically on your data and estimates the cost of each candidate plan and select the best plan, right? And the StarRocks query cost optimizer is natively built and deeply integrated with the execution and the storage layer, right? So this took us around like 2 years to get right, like 3 years ago. We finally got it right, right? Thank you, the StarRocks community, right? And the cost-based optimizer is definitely, I think, the most important factor, into actual scalable and performant join queries. And this is just one thing that our cost-based optimizer is able to do, right? So this is a global runtime filter, right? See here, you have a join, right? See the left table is a fact. The table on the left is a fact table. Table on the right is a dimension table. Let's say the fact table has like a billion rows, and the dimension table has 1,000 rows, right? And you have some kind of a column, with price more than 100, a filter, right? And what if, and that price is probably not even in the column, in the fast scan, right? uh the fact scan table, right? What if you're able to project that filter over the rows that's needed into the fact scan uh table, right? If you're able to do that, you reduce the number of rows to scan on the bigger table from a billion to something a lot smaller, right? For example, like a million rows by sending a SIMD Bloom filter, from the right table to the left table, right? But sending that filter and making that filter actually takes cost too. Um, is it worth it to send it? That is a problem. Our cost-based optimizer has to do, right? And this runtime filter is very, very important for those tracing scenarios because each trace is basically a self join, and it's really, really big self join if you have multiple hops, right? And global runtime filter basically does like most of the heavy lifting. Um, discard like most of the data, right? Without this, it's just impossible. Just scan every single table, it's not going to work, right? So this is very, very important. And then I want to talk about computer architectures, right? So after the query is planned, we have the physical plan, and now it's time to actually execute the query, right? So what you want to do is run those distributed joins at a scale distributed, right? I don't think a lot of your data is going to fit into a single node, right? Right? Unless you're running, like a fact joined very small dimension table where the dimension table fits in the memory, right? If you want to run fast join, you need to worry about computer architecture, right? Does it support actual shuffle distributed join, right? Shuffle join is the key, right? Without the ability to shuffle, you're basically stuck with broadcast join. Basically means your smaller table needs to fit in memory, or you have to do you have to align the key of your distributed key, with the join key, right? So there is like no data shuffling, right? And a lot of the solutions today, such as ClickHouse, such as Apache Druid, they still don't have a shuffling service. So basically, what they run is a scatter gather kind of architecture approach, right? It's very simple, right? But it's not going to be able to support your big table, join big table kind of queries, right? It's gonna always bottleneck. It's always gonna OM, right? And there are other architectures too, right? for example, like MapReduce or stage by stage compute, right? So this has a shuffling service, such as Apache Spark followed this kind of architecture on a high level, right? But each shuffle is persists to disk, right? This is more optimized toward batch processing instead of low latency kind of queries, right? What you want to look for is those MPP architectures, massively parallel processing, shuffle between memories, right? So there is no wait time. So more optimized for low latency join queries at a scale. So this is compute architecture, and then is how we store the data, and CMD, right? We store things in a columnar format. Um, almost all of the analytical databases do. Why? Because we want to store things in batch, right? For a analytical query, it's always you're searching by column, right? And this is true, for CPU processing too, right? Vectorization basically means um, you're you're computing things in memory in column in batches, right? And CMD basically is, with each CPU instruction, we take care of multiple multiplications instead of one per CPU instruction, right? Single instruction, multiple data, right? So this is SIMD, and this is the um, one of the cornerstone, how we get like really good OLAP performance too. The more batch you run, the faster analytical query is gonna go, right? So this is SIMD and vectorization and columnar storage. So this is how quick StarRocks is compared to other solutions on the market, right? So this is the SSB benchmark test. Everything with the multi-table. StarRocks here is the multi-table original SSB test with multiple tables and joins on the fly, aggregations on the fly. And the folks at ClickHouse created a variant of that benchmark test called, just SSB flat, right? So basically, it's a denormalization between all of the tables, and only do the aggregations on the fly instead of doing the joins on the fly as well, right? You can see StarRocks multi-table performance is actually faster than Apache Druid's single table performance. It's almost as fast as ClickHouse single table performance. And of course, StarRocks single table performance is the best out of it all, right? So this means a lot, right? So this means that you don't have to do denormalization. You can actually make join run fast enough, so you don't do denormalization. So you don't have to deal with all of the pipelines. So you don't have to deal with data backfilling when you're trying to do a schema change. And also you can do real-time analytics without actually introducing stream processing, right? Here is a use case. It's Demandbase. It's called Demandbase. It is a account-based go-to-market platform, for B2B enterprises, and this is their kind of like in-product analytics, customer-facing analytics, right? Before they were using ClickHouse. ClickHouse does not join, so they were forced to denormalize everything, right? Data became locked into a single view format, meaning that every time they try to do a schema change, even on a very small table like 1,000 rows, but they have to redo the entire column in the denormalized table. The number of row equal to the biggest fact table, right? That's not very good, right? It's a lot of data to backfill. Very difficult to do a schema change. Also, explode storage, right? For them, resulted in around 10 times waste of storage, and this is around the average, with all of the ClickHouse users we ran into, right? And the denormalization pipeline, of course, it created added overhead. They needed to introduce stream processing, to keep up, with the demand of real time. Um, and just with the number of table they had, real-time analytics on most of their use cases when they were using ClickHouse was basically impractical. They couldn't do it. It's too much cost. Then they moved to CelerData powered by StarRocks, moved to StarRocks, and greatly reduced the need for denormalization, right? So before denormalization, it was a must. And once they moved to StarRocks, yeah, they really didn't like denormalization. I don't even remember they even denormalized anything, right? But this is still available, on demand through StarRocks Motorized View, right? So first, they avoid the storage and compute bloat, right? Because of the ClickHouse drawing limitation, right? A very simplified architecture because no more pre-processing, right? So they can actually go real time in the future, right? And also flexible schema evolution because no more data backfilling because got rid of all of the denormalization pipelines. And real-time mutable data. So how to get second-level data freshness for all of your data, not only the append-only ones, right? So this is StarRocks delete and insert strategy, right? So what StarRocks does is that instead of uh, uh, have a compaction job slowly take care of that in the background with like no acceleration, no indexes, right? StarRocks marks delete during data ingestion. This is pretty normal, right? But we do have a primary key index, a in-memory index, that accelerates the mark delete. So the index basically stores, given a primary key, it maps to a hash of a primary key. It maps to wherever that thing is stored into storage, right? So it can basically locate wherever to delete O1 complexity, right? So there's no merge operation, best possible query performance because everything's resolved, at data ingestion and very cheaply too, right? So you're able to get second level data upserts, directly on columnar storage. And also this is fraction of the storage required and way better performance when you compare to solutions that actually require or rely on a row storage, for data updates, real-time data updates. So this is how StarRocks handles real-time mutable data. And then I'll talk about some use cases, right? So first is Coinbase, right? So they have two scenarios. This is they just presented this work at the Star Summit last month. I'm going to share the YouTube link later in the comment section. So first is their data architecture, right? So they have basically two generalized two data sources, right? So first is more like batch, like workload. They're from Databricks, Unity catalog, governed Delta tables, right? So they do ETLs there, and they use a Spark connector to basically batch the jobs, the data into StarRocks. And they have a lot of real time data, especially for the tracer workload, right? And it basically it's a Kafka connect directly from their services, right? A Kafka connect directly streamed into StarRocks with very like second level data freshness, right? They have two kinds of scenarios. So first is blockchain transaction explored, right? So basically list transaction, two from a given address on a selected blockchain, right? So this is a lot of QPS, right? And this is done on 300 tables, and at the time of the StarRocks Summit, 573 billion rows. Oh, CelerData just shared the Coinbase session in the StarRocks Summit 2025 in the comment section. Please go check it out. And then it's the tracer, right? Basically, it's the tracing kind of scenario we just talked about, right? And then the result is much faster and scalable multi-table queries, when compared to ClickHouse. And they also show some results in the presentation. So definitely do check out the recording. And the next is TRM Labs, right? TRM Labs is another blockchain company, right? So they do customer-facing analytics, right? And they have around 100 terabytes of data that's growing at a rate of 25 to 45% annually, right? And they have a lot of very complex joins and high cardinality aggregations with a 3-second P95 SLA, right? And also they need multi-site deployment. And they were using Google Cloud, right? Google Cloud, BigQuery on top of Google Cloud, and Google Cloud and BigQuery really hits that performance bottleneck, when the scale grows, right? And they were looking for a change. And then they adopted, oh, that image is wrong. I should have changed it. Yeah. Yeah. And then they adopted StarRocks and Apache Iceberg as their new Lakehouse architecture, right? So they considered Trino, StarRocks, and DuckDB, and they benchmark on filtering and complex joins aggregation performance. The result is they have a single source of truth, unified on Apache Iceberg, and running all of the queries directly from Apache Iceberg without any data copying, right? So no more data ingestion, no more many copies of the same data laying around in different places, right? Direct query, and serve their customer-facing efforts, customer-facing analytics efforts, and end up they still got 50% improvements in their P95 latency, right, and 54% reduction on query timeout errors. So this is TRM Labs on StarRocks and Apache Iceberg Lakehouse. And yeah, StarRocks, it probably sounds pretty okay, right? But running a database by yourself can be quite challenging. Here I want to introduce CelerData Cloud BYOC, powered by StarRocks. It is a cloud managed version of StarRocks with advanced cloud features, all deployed in your VPC. The BYOC stands for Bring Your Own Cloud. So basically means that you can see here, you have your data plane, right? That's the data and the cluster, the enterprise StarRocks cluster in your VPC, in your own AWS or GCP or Azure account, right? And we have our own control plane in our VPC that does the maintenance like kind of remotely, right? So you own not only the data, you also own the entire deployment, the CelerData Cloud deployment, right? So, and it has enterprise security and access control, right? All kinds of encryption. You have row level security, right? And also HA and failover mechanisms are available with CelerData Cloud, BYOC, and has all kinds of compliances, right? In Europe, if you're in the US, SOC 2, GDPR, and ISO, and all kinds of compliances, right? And then you have SLA guarantees, by the initiators and the maintainers of the StarRocks project, support from the committers and the TSC members. There is one example feature that CelerData Cloud BYOC has. Physical isolation, this multi-warehouse architecture, right? Storage and compute separated, so you're able to um, deploy multiple compute warehouses that has physically separated CPU, memory, disk, and network I/O, right? So you can you can scale each one of the warehouse, so each one of your workload independently. So you're able to achieve not only, let's say, for example, ingestion, compute separation, but also compute separation across different kind of workloads, right? So this is available on CelerData Cloud BYOC, and we're also open sourcing this feature in the 4.1 release in the next, let's say, 4 to 6 months. Okay, faster blockchain analytics. If that's all sounded interesting to you, please scan the QR code and join the StarRocks Slack community. And if you're interested in CelerData Cloud BYOC, there is a 30-day free trial we're running. Go to cloud.celerdata.com and claim your 30-day free trial. Is there any questions? What is the size of deployment in Coinbase, FECN, and what is the amount of data? Um, I do know the answer, but I'm not sure if I can I can share that. Maybe check the recording if it's there. If it's not there, I don't think I share that. It's not small. Can StarRocks do joins between a native table with real-time ingestion and the Lakehouse table? For example, Iceberg table. Yes, you can. So another question in the QA. Just make them available. For StarRocks OSS, does it have web UI to run query? I don't think so, no. The StarRocks support S3 Iceberg Ice3 or Iceberg or even AWS Glue? How is the performance? Do you have performance benchmark? Yes. Yeah, so S3, Iceberg, and Glue are three kind of components, right? S3 is the physical storage, Iceberg is the table format, and Glue is the catalog. Basically, it's a pointer, tell us like where that Iceberg table metadata lives, right? Yes, we support all three. Uh, for the catalog, if it's REST catalog compatible, something like Lakekeeper, we can support. And yes, we have support table formats such as Apache Iceberg. We have the best support for Apache Iceberg, all of the performance optimizations, but we also have support for Delta Lake and Hudi tables. And we do support S3, yes. AWS S3 or any S3 compatible object storage uh, to persist data in, right? Performance benchmark, it didn't show in this webinar, but if you watch, search on Google, have them, I think, my other webinars, and also the StarRocks keynote, the StarRocks Summit keynote that our TSC chair just did, showed a new benchmark. I think we're around 8 times faster than Trino on TPCD as 1 terabyte. Um, yeah, on top of Apache Iceberg compared to Trino. Next question. Assuming we only have Parquet files on S3. Yes, we support Parquet and ORC. Um, when are you going to release updates and deletes for Iceberg? Is it already supported? I need to double check on that. I need to double check on that. Any other question? I'll get back to you on that. D. Any other question? Oh, by the way, this TRM Labs use case is also there. No, it's not. Okay. I don't think it's in 4.0. Let me go back and check with the Iceberg PM. I'll get back to you on when we plan to release that. What is the scale of nodes like to support multi-terabyte table size to store in Iceberg with join queries? See, that's a very tough question to answer because it not only like the table size doesn't really matter that much, is how much data you scan, right? We are able to prune a lot of data. If you have a where clause there, we can prune that. It's basically like how selective your filters are, mainly, right? Multi-terabyte, it could be, let's say you have 32 core, 8 of them, you can run some pretty serious multi-terabyte, like 10 terabyte down, like within 10 terabyte. But if it's very, very like full table scan, that's gonna need more nodes. But when you think about how many cores, uh, think of if you use something like what is your current um, uh, query engine, if I may ask. Okay. Yeah. So core wise, if you're using Trino, like a third of Trino, I would say start there, or half of Trino, or if you're doing a benchmark, 1 to 1 to make sure it's fair, right? But in production, expect half to a third, depending on like how complex your queries are. The more complex, the bigger the difference. And memory, give enough memory, so we are able to like process most of it in memory, so it's faster. Okay, I think that's all of the questions. Thank you guys so much for joining. See you guys again next time. Thank you. Appreciate that.